So we're going to talk today about engineering change management, and what we're going to do is start with production change, move to requirements change, and then end with requirements evolution. This is actually a presentation that we put together for a visit with Pronova, a proton therapy nuclear cyclotron cancer center system, really big, cool, big stuff. But they were interested in knowing how we handle and what we understood about change management. And so students that contributed to this, because this is all what they've done, not anything that I've done, Prabhu, Bishoy, Shraddha, and now Keith. Though we do have some other students that are now in the room that are moving into this direction and taking a look at what exactly is change management. Okay? So when we talk about engineering change, or ECs, big deal. I mean, engineering change is a huge deal. This is where most companies spend all of their money and all of their time. Okay? And it sometimes is because they're trying to fix problems. Most of the time, they're trying to address stuff that they did not think about before. Okay? So engineering change, fundamental, is found throughout. It's not just in design that you're doing engineering change, but it's also in production that you're doing engineering change. And how we treat it is completely different. But most design is variation. So when we talk about engineering design in general, we're also just talking about much of it is evolutionary. We're going to make a change to this product. And so we're going to introduce some new features. We're going to replace this part with a new part, which makes it lighter weight. It's going to make it cheaper and stuff like that. The challenge is when you do those substitutions, you think that a single part replacement is not going to be a big deal, but then you start thinking about how that replacement part can impact the entire system. Okay? And that's where we really get our problems. And so that's what we're talking about here, and how do we handle and address these. Okay? So we do have a high cost of engineering change. It costs us money. It typically takes about 120 days to implement a change. Okay? That's 4 months. That's a long time. Frequent engineering changes disrupt the manufacturing process. So if you're going and you're saying, hey, we can make this better, let's have this engineering change, that means that you're going to stop production. You're going to have to run a bunch of tests to make sure that it's not going to affect anything. And then you're going to restart. I mean, so it's a lot of issues when you're going through this. Then you have the propagation effect. So if I make this change, and it's going to affect how I do this, and it's going to affect how I do this, and it's going to and the first order you can typically figure out. It's that second order. How did what I do affect that? And then how did that affect other things? Okay? Engineering change is such a fundamental, ubiquitous aspect of production and engineering that it is actually now codified as business processes. All right? It is, companies have standard ways that they allow for engineering change. All right? You guys see this when you do your blueprints and you have all of the different signatures on all your manufacturing prints that have to be approved, right? That is because they want to make sure as many eyes were on that to make sure it was a good and valid change. Okay? Now, think about, that's just in the design phase. In production, it's an even bigger deal. Okay? So between 1/3 to 1/2 of all of your engineering resources are dedicated to engineering change. Imagine what you could do if you could predict this change and address it earlier. You could take all the time and those people that you have dedicated to managing just the change aspect and have them work on new product development, have them work on other things that are actually value adding. So, huge issue. I mean, an incredibly huge issue. So if we look at the basic change propagation issue, we have an initial change, And then that change could create a concern. This concern then leads to another change that you have to implement to address that concern. And that leads to another concern. Okay? And so that's how this propagation change typically occurs. Most of the time, when people talk about the change in that propagation trend, they're focused on parts or components. Okay? So it's component 1 touches component 2. So if I change this, I could wind up with an issue over here. Okay? And that, keep that in mind. That's how most people have viewed change. Ideally, so as an example, we have a new drum brake that we've introduced. But now we start to see some drum failures. So that drum failure, we're going to increase our wall thickness. But by increasing the wall thickness, now we might have reduced the gap clearance, and so we're going to have some new tire punctures. Well, if that then is being seen, then we're going to have to increase the ventilation to allow it to cool so it doesn't expand. So you have that cascade effect. So we want to be able to eventually put up a barrier here. After that very first change, we want to isolate it. We want to make sure that we get this right so it doesn't cascade into new concerns. Okay? And so that is our goal. Our original goal is to focus on in production. Okay? So we are making stuff right now. If I'm going to make a change in production, I want to make sure that it doesn't cascade and affect anything else. All right, so what exactly do I have to do to convince myself that this change is isolated, that it is controlled and contained? Okay? And so we started looking at some other sources for this change. Okay? So where are all these changes coming from? It's not just coming from parameters, and it's not just coming from parts and stuff like that. We found other sources for stuff. Okay? And that's where we're going to go. Okay? With this very first project, we're going to look at line sustaining engineering. Okay? Going to look at how can we help isolate that change. We're going to talk a little bit about a design enabler tool that we developed, that we implemented, and that we've tested in several different companies. But moving beyond that, so that's at the back end, at the end of everything. We're in production, we're making change, we can help that. Can we roll all the way up to the very beginning and handle the changes that are occurring in requirements? If we can handle that, if we can develop some sort of tool to predict the change all the way up here, upstream in the requirements, that's pretty powerful. And so that's a second thing that we'll talk about briefly. And then we'll talk about some of the requirements evolution and issues with requirements. Might not actually get that far in the talk today. So, line sustaining engineering, we're in production, we're making stuff. And now someone comes along, another supplier comes along and says, hey, we can do this part better. Or you have someone else coming in and say, I want you to remove this mass. Or I want. And so now we have to control that. All right? So we're moving beyond the parts and the cascading and how part pathways occur. We're going to also look at other system interactions, such as behaviors. Okay? So it could be that we're looking at thermal issues. You have an engine bay. Within your engine bay, you have a manifold, and you have a windshield wiper fluid reservoir, right? They don't touch. There should be no impact changing one on the other, right? If I change my reservoir, windshield wiper fluid reservoir, and I make it a little bit thinner material, is that going to change the performance on the manifold? Probably not. If I change the manifold and it increases temperature, is that going to have any potential impact on the windshield wiper reservoir. If it's a thin plastic, it might warp, okay? And so depends on how close it is and stuff like that, but there's a behavior relationship between the parts even though there's no physical connection. And so that kind of leads into the ambient pathway. And then we also have this external interface type, and this is where organizationally we have one supplier giving you lots of different parts. If that same supplier offers to make another part where you're getting it from a different supplier, is that going to change things? Or I take that part, that contract away from supplier A and give it to supplier B. Even though they're making the exact same thing, is there the potential for there to be a cascade, a change impact? Most certainly. And so now we need to figure out, how do we control this? The best way to control this is to go ahead and develop some good tests up front. And so we're going to develop a very controlled verification, validation, test planning approach. Okay, it's not going to be an automated tool, but it's going to be a tool that guides the engineers through this to make sure that you've thought through all the different issues so that you have a smaller set of tests to run, not the exhausted everything set of tests. All right, and so we're going to approach it very similar to a V diagram, where we're starting at the high level system and come down to the low level components. And we're going to look at different issues and requirements. Okay, so the first thing that you want to do, if you have a change in the brake drum, you probably want to roll up one level to the brake system. Okay, if you know you have a change to the system, you want to go up one more level. Okay, so we're always looking at that level and up one. Okay, does that make sense? You want to identify those requirements that are associated with those levels. Unfortunately, where are those requirements going to reside? If you're in production and you're working at the manufacturing plant, do you have those requirements? You may not even have access to those requirements. So you're going to have to come up with some of those requirements on your own, unfortunately. So that's the first step. We want to identify those requirements. Ideally, pull them from an existing document. Otherwise, articulate them yourself. And so in this case, we may have some performance requirements, stopping distance after a downhill test, brake lining life, these type of things. And so we populate that. Now, the things I'm going to show you in yellow are going to be the manual data entry that you go through. The things that are in gray are going to be these automated in the tool. Okay, so this is information, great automation, it counts the number of rows that you just filled in. Okay, so we have some requirements, and we can start looking at now the systems interaction. Okay, from the system interaction, we're going to explode out. First, looking at our internal system. And then, like I said, we go one step out of that, and that's your external system. Okay? We are most interested in the brake lining. Okay? And we look at the level of interactions. Okay? So the brake lining is directly related to A, the foundation brake. The brake lining is also directed to B, the brake drum. It's indirectly related to C, the slack adjuster. So there's one intermediary between them. And you can set this, you can return the number of interactions, the depth of interaction, 1, 2, 3, 4, okay? And we've done some other tests and everything. We found saturation typically occurs at 3 or 4. Okay, so 1 or 2. 2 is what we think is the appropriate level for you to focus on. So once you have that, we're going to identify these interacting parts and the order, that the depth at which we're going to be concerned. Okay, so we pull it out for brake lining. And now we're going to look at the organizational aspects. Okay, so for the wheel rim, we have two different suppliers for the wheel rim. So these are companies that are giving us the parts. Supplier A supplies wheel rim variant 1 and wheel rim variant 2. Whereas supplier B is our backup and they supply only variant 1. Okay? So if I make a change to the wheel rim, or I make a change to something that might affect the wheel rim, now how many different variants do I have? How many different configurations do I have to test? Well, I probably want to look at variants that are coming from the supplier A and variant coming from supplier B. Probably. Definitely, if I gave you a little bit more information and said that variant A, or supplier A variant 1 is 95% of our purchase, and supplier B variant 1 is only 5% of our purchase, do you really think we have to worry about B? Maybe not. Okay, and so this isn't going to tell you exactly what tests you have to run, but it's going to expose the issues so that you can make that case and argue within a design team and a review. Okay? So we're going to identify these possible combinations. And those combinations going from that flow chart, we can plug them in here and we can get the variant vectors. And now we can start to make some decisions on which combination vector we actually need to worry about. As we have more parts and as we have more suppliers and as we have more variants, that list is going to grow very long. As an example, with BMW, you might have 7 million different possible X5s that are being produced. How many test cars do you actually have to build to verify that everything is buildable? All right, I mean, that's at the maximum extreme here. Okay? So in this case, we can go through and filter and say, well, we're not as concerned with this supplier because it's a very low volume. We're not concerned about this variant because this variant is never actually an option with this other variant. All right, so you can eliminate a few things, and maybe that's how we eliminate it, and we keep only these two variants. Okay? Now we have to go back to the requirements and the tests. So typically you have a set of validation tests that your OEM requires of the supplier, this supplier requires of the sub-supplier, and back and forth. And so you may have some sort of test. It's a vehicle level test, distance. Now if it's a vehicle level test, that means I have to put this subassembly on the complete vehicle. Now I have to do is that going to be a cheap test or an expensive test? It's going to be an expensive test. And so we have some additional things that we can look at in terms of the cost of the tests. And the cost of that test may be extremely high, but then, it is required for legal certification. Can you avoid doing that? Maybe not. But might it be possible to pull from that one test several different answers to your requirements? Okay, so what we can do is we can look at our tests and our requirements and see how they relate to each other. Okay? Best practice, when you guys were taught in undergrad classes, you were always told for every requirement you need to have a test. Okay, that's ideal, but oftentimes you can test multiple requirements in one test. Okay, and so if that's the case, we can save a little bit of money if we can find those ideal tests that will cover more requirements. Okay, at the very least, you have to have at least one relationship for the requirement to the test. Okay, if there's a lot of overlap here, then you can start to figure out which test will give you the most information for the lowest value. So you can do a cost-benefit analysis. Now we start laying out the actual protocol, the test plan. There's a lot of meta information here for tracking purposes and making sure that everyone that needs to be involved in this test plan was involved in the test plan. You have your requirements, automatically populated, which combination vectors, and then is it legal or not legal? And then you can start assigning responsibility and deadlines and stuff like that. Okay? And so from this point of view, this is a tool to guide people through the decision-making process on which tests need to be done for which kinds of configurations under the change that is being proposed. We have our baseline, and we can start to now ask questions about the strategy. Are you going to be looking at a specific target, or it should be as good as the other existing, or whatever? But this is where everything becomes really interesting. We want to start to do a trade-off analysis to figure out which tests we want to do in what priority level. Okay? So, if I can identify a test that is a cheap test that can be done early but could expose issues, then I can stop. I don't have to complete the rest of the test suite, right? If I identify a test that takes a long period of time but doesn't expose as many issues, then that's you want to look at that kind of as a low value test. Okay, and so this is one point of view for you to look at, lead time versus test, cost versus test. We have different tests and different iterations, and sometimes we have to do multiple runs of one test. Sometimes we can get away with doing only one run for a test, and we can get different rankings, and we can say, all right, in this configuration, requirement 2, we can nail really well with these tests. Requirement 3, we need to work on a little bit more. Okay? So, that's kind of high level, laying it out, more details, read Prabu's thesis. But we went and we developed this tool, implemented this tool, and took it to International Truck. Okay? And that was kind of the motivating behind it. In this case, we are looking at previously executed changes. So this is a Pastori case study. Okay? And we're looking at, I won't give the details here, but the actual situation is that they're making school buses, okay, U.S. school buses, and you have on the floorboard, the floor of most school buses are actually wood, okay, or some composite wood. And you have nuts and bolts that are holding it together. Great. Well, someone came along and said, hey, I want to offer up, let's use some better quality composite wood. All right? Does that sound like it would affect anything? No problem. All right, we're going to use higher quality, which means that that wood is going to last longer, and we're going to be able to make people happy. Super, let's do that. Someone else comes along and says, well, we're having a problem with some of our nuts and bolts on the underside of the frame rusting out too quickly, so let's go ahead and get some galvanized bolts, and we'll use those galvanized bolts to attach the floor. Is that an issue? Okay, 2 changes, not a problem. However, those 2 changes occurred at the same time. With those 2 changes occurring at the same time, what they discovered was that the treatment in the composite wood interacted with the galvanization of the bolts. Okay? And that chemical reaction actually tore out or wore out, corroded, that's the right word, corroded around the bolts very quickly. So instead of their brand new, longer life floorboards, they wound up with floorboards that lasted a couple months. Okay? And this was a change that occurred that individually, they just looked at it through blinders and said, this change works. Looked at the next one through blinders, this change works, let's just do it. A very simple test could have prevented all of this if they had just said, why don't we take that floor option, the higher grade option, and the galvanized bolt option, put it together and see what happens. Okay? And so, in retrospectively applying the method, walking through it with the engineers that were involved, they were able to actually identify simple tests that would have caught everything. You know, this is, albeit a little bit omniscient because it's retrospective. Okay, so, but it served, could have served a really good thing. They have since implemented this, and it's considered best practice down at the plant in Florida, where the manager and where Purdue was doing an internship, and that manager has now been tasked with implementing this tool in all of the international truck facilities. Okay? But again, like I said, this is a posteriori case study. Let's take a look at a in-process case study. Okay, so this is with Reliable Sprinkler, not an automotive company. They're up here in Easley, and they make sprinkler systems, commercial industrial sprinkler systems. They're wanting to introduce a new product, new valve system, and we did a workshop with them. Went up there, we walked them through this process. And in walking them through this process, they identified a test that they had previously scheduled to occur at the end of their product verification release, that they scratched their head and said, well, why don't we do that at the beginning? Okay? In implementing that test at the beginning, they were able to identify a design flaw, okay? And they didn't have to wait the 6 months to conduct the other tests. They were able to fix the design flaw, rerun that cheap test, and then were able to verify. Okay, so they effectively saved at least 6 months of product development time by looking at the tests, reprioritizing the tests, and figuring out how to strategically align them. Okay? So we can see that there's some value in looking at in production, changes and trying to contain it. Okay? The real question is, can we do this in design? So engineering changes that occur during the design process occur constantly. The fact that you are designing means that you're changing. So we don't want to document all of that. That becomes exhaustive. People have tried this in the past. They've tried it with design rationale systems and passive capture and IBIS systems and stuff like that. Okay? But we do know that there are changes that do occur that are recorded. Okay? And we're going to look at one of those through a case study done with AEC, Automation Engineering Corporation, up in Greenville. They are an engineer-to-order company. Okay, so they are an automation company that designs and makes production equipment, assembly lines, work cells, stuff like that. Okay? Well, they're making this for BMW or Michelin or whoever else. That means that they have a contract. What exactly is a contract from the point of view of engineering parlance? It's your requirements, right? Now, if you make a change to a contract, do you think you have to document that? You have to make sure everyone knows that you're documenting it, right? Perfect. We have contract, that is our requirements, and we have any change that comes along has to be approved, which means it has to be documented, which now means we have our engineering change notification. Okay, got it? So that's what we're going to look at here. So let's start with big picture, engineering change propagation methods. Like I said at the very beginning, these are all components, and these components are all touching, related, connected to these other components. And most people look at the change that might occur to this guy and how it propagates to these guys, and then it might propagate beyond. Okay? But that's at the component level. If you have your contract, do you have any components defined yet? No. So we're much earlier. We want to know, can we move this upstream? So we don't know what is affected if we don't have components. Many different relators, which should be used. All of this is done in the physical domain. Can we move beyond the physical domain? So let's consider these components again. But around every component, you actually have a set of requirements, right? And instead of relating the components to each other, if you related the requirements to each other, then if I have a change here, it's going to change only these requirements because those are the dimensional requirements that are affected, or those are the material requirements that are affected with this change. Now we have a different set of relations that we can trace out. All right? But how do we relate requirements? Relating components are fine. Component A touches component B. Even organizationally, component A came from McMaster, component B came from McMaster. How do you relate requirements? So that's the key, and we're going second order. So what we're going to do is we're going to look at historical cases, past completed projects at this company. We have their requirements through the contracts. We have the negotiated engineering changes to those contracts. And then we look at the subsequent changes and the subsequent changes to that. Okay? We want to be able to predict off of this first set of change proposals what the next set will be. We want to predict from this what the next set will be. Okay? We have to figure out a way to relate those requirements, and we want to be able to do this so it's not just a specific product or project, but more general. Okay? So we're picking 3 of them to learn from. And we're going to have our engineering change notification, unanticipated change propagation, and a new change notification. So contract change, new contract change. Well, we're interfering or interceding with this. We're interrupting it and saying, all right, this change notification to the contract really relates to these requirements. These requirements we're going to feed into our tool that doesn't yet exist, and we're going to predict what the next set of requirements will change, which will be found in this ECN. Okay? So, first, we can look at manually relating our requirements. So we can look at our contract, extract out that there are basically 250 requirements. So I take 250 requirements, 250 requirements, and I go through and I say, well, this requirement is related to this guy. This guy's related to this guy. This guy's related to this guy. Okay? Essentially what you're doing is you're creating the hat or the roof of QFD. All right? So this is best practice. This is how we can do it. And so in fact, this is considered, closest to current best practice as defined by researchers up at MIT. When we use this approach, we can start to look at which requirements change and see how far, how distant they are from the next requirement that is going to change. And we find that second order relationships are really key here. And we can return a list of requirements. So given this requirement change, here's a list of requirements that will guarantee that the next requirement change is in that list. Make sense? That is this 27%. So we have to go through about 27% of all of the requirements to find the next change. Okay? So if you have 250 requirements, and I give you 70 requirements, you're guaranteed to have the next change. But that means you have to look at all 70 requirements. Does that really help you that much? Okay, so we need to improve on this. Okay, another limitation, it was limited to only one requirement changing at a time. In reality, you have multiple requirements that are changing. Okay. The other thing that we noticed when we did this manually, you aren't selecting any non-nouns. You're only selecting nouns to relate requirements. Adjectives, adverbs, other conditionals, prepositions, or verbs are not incorporated. Are we missing something there? Because effectively what we've done is we've still done the component-based propagation, taking only the nouns from each of the requirements. All right, and then at the end, there really isn't a ranking system. We just return, this is a set. Figure out which ones you're going to find in there. So we decided to go through and figure out other ways to generate these relationships. Okay? So we looked at nouns, verbs, okay? Two ways of doing it. Automatically pulling out all the nouns, first noun found in the requirement, second noun found in the requirement, third noun, fourth noun, fifth noun. First verb, second verb, third verb, fourth verb, and fifth verb. Okay? We also looked at keywords using the manual selection. Okay? A totally separate approach. We actually created a artificial intelligence tool, bag of words, to automatically generate those keywords. And it was actually effective. So we generate these DSMs, and then we're going to do propagation analysis, and we're going to try to figure out all the different permutations and statistically figure out which of the nouns, verbs, relationships, keyword relationships show up the best. Okay? And so we're using a part of speech tagging. We start with our requirement sentence. We tag the first 5 nouns in this sentence. We tag the next set of verbs in the sentence, and then we identify the key words. Okay, and that's the manual process. Now, if you look at it, the key words identified were switch, switch, label, label, connector, connector, fixture. All right, so tag and fixture are the only ones that aren't actually a noun or weren't identified. Okay, so the first 2 totally automated. This third one is still manual. We thought that it would be easy to have people identify some quick keywords for each requirement, okay, if you're only asking them to do 3 or 4 or 5. So now we have to figure out, do we have to ask them to identify 5, or is it okay to identify the first one, second one, third one? All right? Based on all these different permutations, we can create a DSM using only the first noun, or a DSM using the third noun and the second verb, or a DSM using the fifth noun, fourth verb, fifth verb, and first keyword. All right? So we have a lot of different combinations here. 655,000 combinations. And so we create all of these DSMs, and we're trying to figure out which combination of overlaying these DSMs give us the best results. We're going to test for is there a relationship path from what we start with the change in the requirement and what we know eventually is changed? If there's no relationship path, then that doesn't help us, right? Second filter, we're going to score the true positives to false positives. And the third one is to look at the ratio of true positive to true negative or false positive, okay? So that we are trying to go through and get the combinations that will give us as much correct as possible without giving us extra stuff that doesn't help, okay? And we can look at and do all kinds of fun little statistical analysis. And we actually find really good statistical correlations. So there are some sets that give us the best. Okay? In this case, we find that the third keyword gives us really good score. Or second noun, third keyword gives us a good score. Or first and second noun and fifth keyword gives us a good score. So we can use actually all three of these combinations and kind of take the intersection return from each of these. Now what's interesting to note, these verbs never showed up as useful. Okay? The nouns showed up as useful, but not necessarily the subject of the requirement. The extra nouns that are in the requirement statement itself showed up as useful. So we can then look at running and testing this idea on the EVRAZ project. 20 different engineering changes made, 23 requirement changes were made, 5 requirement propagations were predicted. All instances are run against model. And so now, instead of looking through a quarter to almost a third of all the requirements, we can look through maximum in all of our instances less than 13%. Okay, so we've cut that in half. Okay, so we're getting better and we're getting better. Our average search depth is only 5.6% of the requirements. So that's nice. In fact, this engineering change was ranked number 1. We got that requirement change in the first go. It's the top score. We had to go all the way down to the 24th requirement to find that change. Okay, and there were some other evolutions, but basically what we're able to show is that you can take a requirements document, take your initial change as being proposed by the company, and say, hey, if we accept this change, these other requirements will likely change. If I accept it and these might change, we're going to charge you an extra $50,000 to make sure that we're not having to undo other stuff. Okay? And that's the key to the tool. When we applied it, we showed them that we could have predicted some of the changes that propagated. We identified in a couple of them changes that the company accepted, AEC accepted, without charging, that resulted in another $100,000 of cost to AEC that they had to eat. Okay? Whereas if they had seen this, they could have said, no, they would not necessarily know how much it was going to cost, but they could have said, hey, we know this looks like an expensive change. Are you sure you want to go with it? Okay. So we've talked about line sustaining engineering. We've at the very end of the project. We've talked about requirements change at the very beginning of the project. Now, what we're really interested in is looking at how does that change occur throughout the project. Okay, so we're going to look at another case study and the evolution of how requirements within a series of senior design projects, 401 projects, how those requirements changed. Okay? And how does that type of change or behavior of change impact the final product? Okay? So, we have our current process. Typically, we have our problem. We're going to elicit these requirements, and then we're going to have a requirement set. But from our problem, separately, we generate solutions. And then we have our conceptual set. And then we're going to have to tie this together. Okay? And so a lot of times students have a hard time. They look at this and say, those requirements that I did in the first week don't have any bearing on anything. I did it because you told me I had to do it. So what? Okay? I'm just going through the motion. I really care about generating these concepts. Fine. You want me to generate concepts and then compare those concepts against the requirements, I'll do that. Okay? But is it even possible to use the requirements to drive the generation of the concepts? You know, are they even solving the correct problem? We evaluate the concepts, we come up with proposed set. So, one of the things that students over and over and over again ask me when I teach design is, why should we spend the time at the very beginning generating these requirements? Should I spend all the time on generating requirements up front, or should I do it throughout the project? Okay? What do you guys think? Spend the time up front or throughout? Okay, well, let's see what happens. Okay? So, that feedback, does the requirements actually impact, and this is where we're going to go. So, for the case study, we're going to use, in this case, senior design, so 402 on this one, 4 different teams with 4 students each, 11 males, 1 female. This is a project sponsored by Parker Hanfin. Shraddha was actually the design coach, or the grad advisor on this, not the design coach. That was a different project. And in this case, design and build a system automatically splice seals. Okay? Data collection. We're going to collect requirements, documents from the teams every week. Now, it's in senior design. This is a grad student that may be an advisor asking them to do it. How often do you think they actually followed through on this? All right, so it's a little sporadic, but we definitely have the initial set of requirements after the first couple weeks, and we have the final set of requirements. And so we can start to do a before and end comparison. Okay? Subsequently, we have collected additional database of requirement documents that we can actually look at week to week to week. Okay? So we're going to look at completeness and specificity of the requirements, and how does this show up in the actual product. So again, we're looking at the initial and the final week. We have an anticipated pattern. So we're thinking that the completeness and specificity will increase from the initial to the final. Does that make sense? Initially, you probably don't have very complete requirements. At the end, the individual requirement will be much more complete. At the beginning, you probably don't have a lot of very specific information about the requirement. At the end, you should have a lot of specific information. Okay, this makes sense. We're going to use a modified approach proposed by Lamar in terms of coding up the requirements. It was expanded and modified by Choi and Shraddha both. And so we're going to take our requirement and identify the subject. All right? In this case, the design must cool. So the design is the thing that's doing. Must is the modality. So it should or it must. And this is the verb, the predicate phrase. And then we can count up the number of adjuncts. We can count up the number of numerical values. And so we get this, we can take a raw textual statement of a requirement and we can break it up into things, pieces that we can start to count and compare and look at. In terms of completeness, We look at the subject, modality, and the verb phrase. In terms of the specificity, we can look at the number of adjuncts and the number of numerical values that are encoded within the requirement. And we can start to look at the before and after. And luckily, we have 4 different teams doing the same thing. So we start to get some replication. And if we look at which we're missing, okay? So we have the blue at the top are the number of requirements that are listed per team. Of the 16 requirements listed by Team A, 14 of them were missing a subject. So they just had a verb. Probably about 11 of them were missing a modality. Is this essentially a constraint or is this a criteria? We don't know because they didn't write it down. When we look at the final week, again, they have 16 requirements, so they didn't increase the number of requirements, but the number of requirements with missing subject, 0. The number of requirements with the missing modality dropped from 11 down to 6. And so we see that there's an improvement. Okay, they're getting more complete. The other thing that we notice is that no one at the beginning or at the end was missing a verb phrase. Is a verb phrase is really what's telling you what that requirement, I mean, in some of the other data collection, you could actually almost make the case that they're missing a verb phrase because oftentimes they just now put down a keyword rather than the actual requirement. So the basic takeaway, completeness can be used as an internal measure of the project. So if we look at it, we know we're starting off incomplete, but by the end we are finishing much more complete. If at midterm or at an intermediate design review, you actually just looked at the details within the requirements document. No solutions, but the details of the requirements. You might be able to use that to know how far in the project you are. Because we know that there is a change from the initial to the final. Does that make sense? Now we have to figure out, are there clear transition points for the different phases of design, or is there also some correlation with success of the project and stuff like that? So let's look at specificity in terms of the numerical values. Okay, so initial week, we have our teams hitting 8 to 9 requirements that have numerical values. Substantially less than the actual number of requirements that they had. By the end, they increased, everyone increased except Team C. They increased the number of requirements that had numerical values. So Team C had to flip, or they had equal, okay? Team B actually had a reduction in the number of 2 numbers in their requirements, but it was offset by increase of the single variable, single values, okay? So again, specificity changes, it clearly changes. As you add more numerical targets to your requirements, you're probably closer to complete with the project. We don't know what the target is, we don't know what that ratio is, we don't know what the transition or what the shape of that looks like over time though. We can also start looking at some requirements tracing and say, all right, this requirement, this specific requirement changed from A to a final requirement. And so we look at requirement 7 for Team A, cool spliced rings. It did not have a subject, did not have a modal, and its verb was cool, direct object, splice rings, adjunct, nothing. Then we have the design, must, cool, splice rings, in less than or equal to 3 seconds. So we have 2 adjuncts with 1 numerical target. And so if we look at the change type as defined by Morcos, introduction of a new system, we have a subject now. Importance, the modality was changed. And specificity, the adjuncts are changed. So we have 3 different changes that occurred here. We don't know exactly when each of these occurred, okay, but if we have greater resolution, we can figure that out. The syntactical system, necessity, and condition proposed by Lamar, we also pick up on those. And so we can see that there's different kinds of change that are occurring. So at the highest level, we can look at change in terms of additions, deletions, changes. So Team B had 2 requirements that didn't change from beginning to end. They were the only ones that had any requirements that did not change. Everyone else had changed, all of their requirements change. Team D had a lot of added requirements. A lot of added requirements. Everyone else did add requirements. Team C deleted a bunch of requirements. All right? A and B were not too bad. A had the most changes or modifications within a requirement. B had the second most. Okay, so now we have some things that we can look for patterns. Okay? And we can use that information and tie that back to performance. In this case, we didn't. In other case studies, we have. Then we can look at it delving down into the change of the language elements and what is it that is actually changing. Most frequent, most common change was the system. Right? Now let's think about that. You have requirements when you're first starting. Do you know what part of your system is going to do that thing that you're asking it to do? But by the end, do you know? Okay, and so oftentimes that system is just a clarification on the assignment of this requirement belongs to this thing. Okay, the necessity or the modality is a fairly frequent one. The condition is also frequent. Behavior and object are some of the ones that are the lower frequency. And so having this, we can start to project and use, if we get enough examples of projects continuously changing throughout weekly requirements documents, we can start to say, all right, we think that at this point, with this ratio, with this kind of change, you're hitting on something. If you're not hitting at it early enough, then maybe there's an issue. And so we have a few different takeaways. Well, number one, lack of uniformity in requirement solicitation. Okay? Students typically, and I'm totally guilty of this, aren't taught specifically how to document illicit detail requirements. Okay? It is a 5-minute discussion in the middle of class, and that's about it. All right? So maybe we need to do more to that. Maybe we could start using the students themselves to score their requirements documents in terms of completeness and specificity. And they then can see that change themselves. And they can see that as they're progressing on their project, they are making progress. 2 specific requirements may not really be able to be met. Okay, and so this is a slippery slope. If you jump and you say, this requirement is that it has to operate under this condition, under this condition, under this condition, under this condition, in this way, for this duration, you can't even test it in most situations. All right, and so that requirement's not terribly useful. So there's also probably an upper bound on specificity. Okay. At the end, students do need to understand this importance of the requirements changing. Okay? I'm going to actually stop here.